I think we could agree that damage could be caused by UV or X-rays. There's certain types of chemicals that can cause this situation in DNA. Usually that could lead to mutations. In the event that there's an error, nuclease, which again with the ase ending means it's going to be another enzyme, it will cut out and replace damaged pieces of DNA. Okay, so the last thing I want to get into real quick is talking about limitations of DNA polymerase, and specifically in linear chromosomes. So with DNA polymerase and linear chromosomes, we could have a problem. If you think about it, DNA polymerase is unable to complete the 5' ends. And see, the reason for that is because if you think about the 5' end, like it would be extremely difficult to ever be able to copy that. Let me show you real quick. Going back to this picture, and there's of course no need to draw it again, but again, you can go in the 5 to 3 direction, which wouldn't be a problem, correct? But imagine we get to the point where this was the end, and you can't open it up anymore. Like, let's say that you open all of it up and that's it. There would be no way, since you can't go, obviously, this on this bottom strand, you can't add a new strand complementary to it going in this direction to my left. Agreed? So you know that you're always having to take these DNA polymerases and make these Okazaki fragments by doing a motion like this. In fact, it started over here. And then the next DNA polymerase would come over here, jump ahead, and come back. And so we could expect the next one to jump ahead and go back this way. And as you could agree, there would be a point in time where it keeps falling off the strand, but there's some pieces that never get copied. Do you understand that motion, that logic? So you're going to have this problem with shorter sides, shorter ends of the DNA. So it says DNA polymerase is unable to complete the 5' end pieces, which means that this would cause over time shorter DNA molecules. And there's somewhat of a fix for our cells, and I say that, somewhat of a fix. At the end of eukaryotic chromosomes. We have nucleotide sequences. Of course, they're made of DNA. And they're called telomeres. And if you think about it, if we're gonna notoriously be unable to complete our replication at the ends of these molecules, then it would be horrible to set an important gene like the gene for, and I'm making this up, but the gene for breathing at the end. Does that make sense? Like, it's much like having a cliff that you know each year there's rocks on the cliff that are falling down, and it's like causing erosion of this much of the cliff each year. Okay, so would you build your house this far away from the edge? No, because within some amount of time, your house would fall over. Agreed? So you would move your house way far away. And that's kind of what our cells do, is they make sure that all the important genes are far away from the ends of the chromosome. Right? And then another thing happens with the telomeres is that when we are there's points and times in which we add what I would call excessive, wasteful, non-sensible nucleotides at the end of our chromosome, so that when they do erode, they're eroding off worthless stuff. It's like saying that Campbell and Reese will erode, so we put the absolute most meaningless chapter at the very end of it. Because if that falls off, well, it was meaningless anyway. Good? So that's why we say that telomeres have, there's these nucleotide sequences. They are not coding for genes, obviously. And they don't stop erosion, they just cause an erosion of something that is really not important. We could also say that as telomeres shorten, individuals age. So it's like a really hot topic in like aging stuff. It's kind of interesting, at least. Another thing to mention, one last thing about this, is the enzyme telomerase, which causes the lengthening of telomeres in germ cells. Germ cells. Germ cells, the gamete cells. Cool? So that would be great, because that would mean that your child is going to be born with these full telomeres. It's like all this potential to erode, basically. Makes sense? And as they live their 80 years, their DNA will erode, and it may perhaps erode into a vital gene along the way. Unlikely, but it may if they live long enough. Cool? They actually believe that telomerase activity is something that's found in cancer. So it's kind of a unique idea. Usually most cells would eventually stop. Their lineage would stop because they've run out of nucleotides to erode, essentially. Cancer cells, they have the ability to turn on telomerase, which means their cells could stay around indefinitely, which is why the tumors would be there permanently. Right? So each cell has like a limitation on the number of times its lineage can divide, if you think about it. But turning on telomerase would allow it to divide indefinitely, which that's true. So that means that, no, seriously. Well, it doesn't give you cancer. Cancer, when cancer's on, then this gene's on. That's going to keep cancer that will allow cancer cells to be just that, cancer cells, to divide uncontrollably. Cool? Okay, the other thing that we'll get into a little bit later on, more specifically in a couple of chapters, is this idea of chromatin in chromosomes. But you know chromatin is made of DNA and protein, right? Right. So I think we're cool with that. And then chromosomes are just condensed forms of it.